Okay, equilibrium. This is the big daddy. This is the concept that we probably will see the most questions from or the most points from, because it really is going to be two different chapters, but both on the same basic idea. So the things we're going to start to learn today, super important. I know I say that a lot, but they really are, and it really will end up being of great importance to you. So again, let's get off on the right foot. Things you understand, good. Things you don't understand, make sure you make notations of them, make sure you ask the questions, make sure you do what you are supposed to be doing, and it will be a lot more enjoyable for you. A lot of people really like the equilibrium chapter. I personally love these types of problems. Maybe not all of the ones we're just going to start today. The ones we'll do today are pretty straightforward, pretty basic, but the problems we're going to get into, they can be really, gratifying when you get to the end of them, and that there's a lot to be said for that. So let's go ahead and get into it. Actually, our lab that we just finished is really going to help you with the first part of what we're going to get into. Maybe not so much this dynamic equilibrium stuff, but the stuff I'll show you in just a second. So let's just start by reviewing dynamic equilibrium. If you remember back when we did vapor pressure, we talked about dynamic equilibrium. And what dynamic equilibrium was when we talked about vapor pressure was it was when the rate of evaporation was equal to the rate of condensation in a sealed container. And when those rates equalized, we were at a point called dynamic equilibrium. And there's actually a ton of different types of dynamic equilibriums. Number one on your paper there is the one I was just referring to. That's the type you've learned before, but that's not the only type of dynamic equilibrium. You can get dynamic equilibrium in a saturated solution. Remember, saturated means you've dissolved as much solid as possible. So if you put any more in, the solid's just going to sit at the bottom because it's been dissolved. But technically, it doesn't just sit there. It actually is dissolving, but at the same time, some of the solvent's dissolving, some of the solute, solid, is dissolving. Some of the stuff that was already dissolved is going back into being in the solid. So it's going back and forth in between aqueous and solid form. You can't see it with your eyes. To your eyes, it looks like there's just a pile of solid sitting at the bottom, but it actually is in a system of dynamic equilibrium. Or like in a weak electrolyte, like a weak acid or a weak base. We talked about the fact that they don't completely dissociate. They only partially dissociate, but technically the dissociation is constantly happening. It's just some of them are dissociating while others are recombining back into the weak acid or weak base molecule at the same rate. So we're going to be talking about equilibrium as a whole, but I just kind of wanted to give you a refresher on the whole concept of dynamic equilibrium. Now, this is the part where our lab actually will really help you, and students in the past that didn't have that lab, they didn't have this knowledge to go off of. We just finished a lab in which we graphed volume versus time, okay, or volume, as the reaction was occurring. And the idea of kinetics was about that part in the curve. So if you remember your curve, it went up straight and then it kind of tapered off. Okay, that's what we were just doing. So this right here represents the products being formed. Okay, we graphed that concentration versus time. If I, on the same graph, put the reactants and what they look like, we didn't do it in our lab, but if we had been measuring the reactant concentration as the lab had been going on, we would have seen the reactants decreasing and then eventually leveling off. Okay, same idea as what we talked about with products. I mean, you're going to make products as time goes on, the rate slows down. Same thing with the reactants, you're going to use up reactants, and as time goes on, the rate is going to slow down. Now, what the interesting part is, let me get a better color, is this whole segment up to about here. Okay, that part right there, that is what we call the kinetics part of the graph. That is when the rate was changing. Okay, that's what kinetics was studying, how different factors affect how fast the rate is happening. But notice what happens right when we get past this highlighted region. Notice this line is very constant. Notice this line is very constant. Once you hit constant rates, no changing in your concentration anymore, flat line, again indicating no rate, that part of the graph, so here, is equilibrium. Okay, and remember, they're still going to be going back and forth. They're just going back and forth at equal rates. So we are now in a state of equilibrium. So your graph that we did in class, we really made it probably about, most of you probably made it about here, where it started to equalize. So you had started the process of equilibrium in your lab. And that's really what we're going to be talking about and what we're going to be going over in this unit. So that graph, again, hopefully gives you kind of an idea of what's happening. I've actually seen in some of the new documentations for the AP test, I've actually seen this graph on some of the practice test questions and stuff. So it's important to understand that where the slope is changing, that's kinetics. When it flattens out, that's equilibrium. Okay. All right, now you're going to be happy maybe to know that there's something called equilibrium law. Just like there's something called rate law. Rate law has to do with kinetics. Equilibrium law has to do with the equilibrium part, the flat part. I say maybe because some of you, you have to work at getting the rate law. You had to figure out what X was, what Y was, what K was. Well, here's the good news. Equilibrium law, much, much easier. Like ridiculously easier. Okay? What the equilibrium law is in a very, very simplistic, oh no, way. Hold on. Be right back.